Welcome to Spaceverse, your portal to cosmic adventures. Here we see an astronaut walking on the moon's surface, but imagine the moon was submerged at the bottom of a colossal swimming pool. This is actually how NASA astronauts are preparing for their upcoming moon mission. It might look entertaining, but the mission is far more challenging than it appears. First, let's clarify that NASA's simulated moon is situated at the bottom of a large swimming pool within the Johnson Space Center in Houston, Texas. Officially called the Neutral Buoyancy Laboratory, this pool measures 202 feet in length, 102 feet in width, and 40 feet in depth, with a capacity of 6.2 million gallons. The water is similar to standard chlorinated pool water and maintained at around 86 degrees Fahrenheit or 30 degrees Celsius. The pool features more than just a moon replica. It also includes a full-scale model of the International Space Station, where NASA practices microgravity spacewalks. Additionally, there is an Orion capsule on the pool's surface used for training water landings for when astronauts return from the moon. Water is the most effective medium available on Earth for simulating the conditions of outer space. This method was first explored by NASA in the 1960s. At that time, following the first Soviet and American spacewalks in 1965, it became apparent to scientists on both sides of the space race that maneuvering in a microgravity environment was far more complex than anyone had anticipated. This realization underscored the necessity for astronauts to undergo rigorous training on Earth in order to perform meaningful tasks in space. Similarly, training for walking on the moon involves additional complications, which we'll delve into shortly. It's crucial to understand that you can't simply place an astronaut in a spacesuit and drop them into a pool, expecting it to work as a perfect simulation. The primary issue is that the suit, which is inflated much like an inner tube, will naturally float. While floating is problematic, simply letting the spacesuit sink isn't the solution either. Achieving the correct balance of buoyancy is what's meant by the term neutral buoyancy. To replicate the experience of zero gravity, similar to what astronauts encounter during an ISS spacewalk, it's necessary to adjust the suit and the astronaut until they reach a state where they neither sink nor float. They are in a state of neutral buoyancy. This balance is primarily achieved by adding weights to various parts of the spacesuit, such as the arms, legs, and torso. Additionally, foam is sometimes used to strategically introduce buoyancy, ensuring an even distribution across the suit. When simulating the moon's environment, however, achieving perfectly neutral buoyancy, which equates to 0 g, is not sufficient. Instead, the goal is to closely mimic the moon's gravity, which is 1/6 of Earth's gravity. This process becomes more complex because it involves creating a center of gravity for the astronaut that closely mirrors the conditions of a real moon mission. This way, when astronauts transition from the pool environment to the actual moon, they won't be disoriented by the differences in gravitational forces. However, since we are currently working within a pool, the astronaut also has to contend with a center of buoyancy in addition to their center of gravity. These two forces can conflict with each other if they are not properly balanced. It is important to understand that walking on the moon is not easier than walking on Earth simply because the moon has lower gravity. In fact, it is significantly more challenging to walk on the moon. This difficulty explains why many Apollo astronauts experienced frequent falls. To grasp this concept, it helps to differentiate between weight, mass, and inertia. On the moon, your weight on a scale would read as 1/6 of what it does on Earth, but this does not alter the physical mass of your body. The total mass of your body, comprising muscle, blood, and bones, remains the same regardless of your location in the universe. Consequently, your inertia also stays constant. In simple terms, inertia is the body's tendency to resist changes in velocity. This means that the energy required to accelerate into a sprint, as well as the energy needed to decelerate, is directly related to inertia. You must exert the same amount of energy to move or stop on the moon as you do on Earth. Complicating things further, on Earth, your weight aids in gaining traction against the ground, allowing you to push your mass in a new direction. On the moon, with significantly less gravity, you have much less traction but still need to exert the same force of inertia. This results in a tendency to lean too far forward when attempting to move, leading to foot slippage and poor traction. This explanation helps clarify why astronauts spent so much time on the moon falling and why NASA is diligently preparing the next generation of lunar explorers to tackle these mobility challenges. The key difference with the Artemis missions compared to Apollo is the extended duration on the moon. Astronauts will spend up to a week on the lunar surface, performing moonwalks almost daily. They must be capable of remaining mobile for prolonged periods without excessive fatigue or causing significant damage to their equipment due to frequent falls. To prepare, lunar explorers will first need to don their spacesuits. NASA has been utilizing the design of the XEMU, or Exploration Extravehicular Mobility Unit. These suits differ significantly from the EVA suits used for spacewalks on the ISS. The current version of the suit was designed and manufactured by Axiom Space specifically for NASA, and NASA has been testing the Axiom lunar suit in the Neutral Buoyancy Lab since January 2024. The internal pressure of the suit is set between 4 and 6 psi, with NASA still experimenting to determine the ideal level. The goal is to strike a balance between maintaining atmospheric conditions and ensuring flexibility. On Earth, the ambient pressure is around 14 psi, and inflating the spacesuit to this level would make it too rigid, hindering the astronaut's mobility. Conversely, if the pressure is too low, as it would be in a vacuum environment like the Moon, it could be fatal. Thus, finding the right pressure balance is crucial. Pressure also plays a significant role during moonwalks underwater. Astronauts will spend 6 hours submerged 40 feet underwater, which can potentially cause decompression sickness, also known as the bends. This condition results from excess nitrogen being absorbed into the blood at higher pressures and then forming bubbles around joints, the spinal cord, and the brain as the pressure decreases. To mitigate the bends, NASA provides astronauts with a special air mixture that has a higher concentration of oxygen and a lower level of nitrogen compared to regular air, which is 78% nitrogen and 21% oxygen. The underwater air mixture contains approximately 46% oxygen, allowing astronauts to spend extended periods on the bottom and return to the surface without the need for gradual ascent like scuba divers. With everything in place, the astronauts will be lowered into a low-fidelity mock-up of the SpaceX Starship human landing system. This mock-up is essentially a large 9-meter diameter circle with a simulated airlock through which the astronauts will emerge. They will then walk over to a simulated elevator platform. While the actual Starship will lower them 30 feet to the Moon's surface, in the pool, they will simply walk straight out and down a ramp. The Moon's surface in the pool is constructed with simulated rock structures, and the ground is covered with a type of sand that mimics lunar regolith or moondust. Once the astronauts are on this simulated surface, they will perform tasks similar to those planned for the Artemis 3 mission. This includes pushing a handcart filled with tools for collecting ground samples, picking up rocks, chipping away at boulders, and digging into the lunar soil. The astronauts will also practice technical maintenance activities such as detaching and reattaching hoses. For added authenticity, NASA has recreated the lighting conditions that astronauts will encounter at the South Pole of the Moon. Unlike the Apollo landing sites, which were near the lunar equator and experienced direct sunlight during the lunar day, the South Pole region presents much more dramatic lighting conditions. The sun only appears from a very low angle, similar to what we see very early or very late in the day. This results in extremely long and dark shadows. To prepare astronauts for these challenging lighting conditions, NASA has been developing a new lunar lighting simulator at the bottom of the 40-foot deep pool. Achieving the desired effect involved turning off all facility lights, installing black curtains on the pool walls to reduce reflections, and using a powerful underwater cinematic lamp to create the conditions accurately. Although there aren't many images available yet, this setup should provide a clearer idea of what video from the Artemis missions will look like. The visual will be significantly different from the classic Apollo images and much more dramatic. Additionally, Artemis will investigate the floors of ancient lunar craters that have never been exposed to sunlight, adding another challenge for NASA to prepare astronauts for. This is where all of it will take place, on a simulated moon at the bottom of a giant pool. Now you know. And that's it. Thanks for joining us on this dive into NASA's lunar training. From simulating moonwalks in a giant pool to preparing for the extreme lighting of the Moon's South Pole, we've seen how astronauts get ready for the challenges of space. If you enjoyed this exploration of the Spaceverse, don't forget to like, subscribe, and hit the bell for more out-of-this-world content. Until next time, keep reaching for the stars.